Today, I would like to share some insights with you on how you can increase the durability and lifetime of your sensor device. My name is Timo Seybel and I work as an application engineer at Gore and Associates. Gore is a material science company with headquarters in the US and has a global footprint with operations and customers all around the world. We are specialists in microporous ePTFE-based materials and provide a variety of solutions for outdoor garments, medical devices and industrial applications. Protecting an enclosure against environmental impacts is not a new topic. Hardware developers are facing this challenge for years already. Today, the big trends in the electronic and IoT industry, as well as rising user expectations, are reinforcing the need to implement sophisticated protective measures. You are all familiar with major trends in the global markets, and I will not spend too much time here. I just want to share two examples and their impact on the design of sensor products. Miniaturization. The desire to design and build sensor enclosures smaller and more compact implements the integration of more electronic components in limited available space. More heat is produced inside the enclosure, the pressure on the seals will increase and needs to be balanced with the environment relatively fast. Smartification. Sensors are taking over more and more functionalities like data evaluation and data storage. Sensors not only provide data in real time, but they also process this data. Sensor makers need to make sure that the devices work perfectly and reliably in the most challenging environments. Customers and end users are expecting error-free operation with highest accuracy. Maintenance should be kept to a minimum and the lifetime, especially in industrial applications, is often expected to be 15 years and more. High ingress protection is becoming a standard for many devices in order to use them in a variety of end applications and in regions all around the world. As a sensor manufacturer, you should consider those expectations during the design phase of your enclosure. With that, I would like to ask why electronic enclosures need to be vented. The purpose of venting outdoor electronic enclosures is to equalize internal pressure differentials. This will extend the reliability and the service life of the enclosure and the electronics within the enclosure. Outdoor enclosures are continuously exposed to harsh environments, such as rainstorms, dust, sand, and wind. During changing environmental conditions, pressure builds up inside the enclosure, which is causing stress on the seals. Over time, this stress will cause seals to fail, which allows water, corrosive liquids, dust, and other particulates to enter the enclosure and damage internal electronics. Protective vents equalize this pressure by allowing air to flow through the ePTFE membrane into and out of the sealed enclosure. At the same time, the vent is a durable barrier to protect the inside electronics from contaminants such as water and dust. What is the source behind our innovation? PTFE is the abbreviation for polytetrafluoroethylene, which is a polymer composed of a carbon backbone and fluorine attached. It contains up to tens of thousands CF2 units per chain. To ensure quality and performance under harsh conditions, the material features a low dielectric constant, low friction, thermal resistancy, UV resistancy, chemically inert, expandable, and oleophobic and hydrophobic properties. An ePTFE membrane is created when PTFE is expanded, creating a microporous structure with a high strength-to-weight ratio while maintaining all of the properties of PTFE. It is not only durable but also highly moldable as well. The unique structure of fibrils, nodes, and pores allows a smooth airflow but can also block liquids and particles from entering. For electronic enclosure applications, ePTFE helps deliver optimized solutions for venting components that are present throughout several industries. A typical application for venting solutions is outdoor lighting. In addition to subjects like design and energy consumption, the reliability and longevity of outdoor luminaires play a major role for luminaire manufacturers. A high degree of IP protection like IP65 enable maintenance cycles to be extended and lifetime expectations of 100,000 operational hours and more to be met. Venting provide and maintain high IP protection levels and thus make a valuable contribution to the overall reliability of the luminaire. The telecommunication industry has very similar requirements. Lifetime and long maintenance intervals are critical factors in the buying process of such devices. But coming back to sensor applications. Manufacturers are usually faced with a number of challenges. Here are a few examples. Rapid temperature change. In this example, we see a forklift truck with sensing devices in a cooling house application. The movement of the forklift between warm and cold zones mean a temperature shock for sensor and the electronics. Here we see an example of electronics and sensors under a cleaning process in a production hall with high pressure washing cycles. Or here, environmental sensors which needs to be protected against liquids, dust and environmental contaminants, but the sensor should not compromise its response time. And finally, space limitations for the integration of a protection membrane due to very compact sensor design. These are real challenges in the field of sensor applications. Suitable venting solutions must show exceptional characteristics in order to provide proper protection and performance. An important vent characteristic is its airflow. Airflow is simply the amount of air that passes through the vent when there is a differential pressure on either side of the vent. This key measure relates to the pressure equalization performance of the vent. Higher airflow means faster pressure equalization or lower peak pressure in the enclosure. The water entry pressure, or WEP, is a value of the minimum pressure required to force water through the membrane. With that, WEP is the characteristic which defines the water resistancy of the vent. A common characteristic is how well a membrane repels water and oils. We differentiate between hydrophobic and oleophobic membranes. Hydrophobic ones are water repellent and oleophobic ones are oil repellent. Oleophobic membranes are capable of repelling fluids with low surface tension, such as oil, soap, and various alcohol compounds. As mentioned before, PTFE is highly inert, and with that, it allows the vent to resist many common chemicals that may encounter an application. ePTFE has also an excellent thermal resistancy between as minus 180 up to plus 260 degrees Celsius. The vent's operational temperature is determined by the other components of the vent, such as the O-ring or the pressure-sensitive adhesive. This typically is between minus 40 up to plus 125 degrees Celsius. And last but not least, the IP rating. IP stands for ingress protection and measures how well a device is protected from solid objects and liquids. A standardized rating scale is defined by the International Electrochemical Commission. An IP rating consists of 2 digits. The first digit tells us how well the product is protected from solid objects, and the second digit is about resistance to water. The higher the rating, the better a product is protected. All vents reach the highest level of protection against solid objects of 6. That means that literally no dust particulates will pass the membrane and enter the enclosure. When it comes to the protection against water, the vents provide a liquid protection of IP64 up to IP69K. This is from low pressure water up to high pressure water jets. They can also be submerged up to 2 meters underwater for 60 minutes, which is defined under IP67 and IP68. With that, venting can provide very high levels of protection for outdoor sensor applications, but at the same time it allows the sensor device to breathe. Now, after we heard about the level of protection, how do I know which vent suits my specific application? That can be simulated based on your specific case. Let's take an IoT sensor installed on top of a mobile antenna, as a use case here. The device is made of plastic and has a free air volume of approximately 100 milliliters. In summer, it can heat up to 65 degrees Celsius due to sun radiation and rapidly cool down during a thunderstorm to 15 degrees Celsius. This temperature change will create internal underpressure in the device and needs to be equalized. In order to find a suitable vent for this specific case, the pressure behavior can be simulated. The result of a simulation will come in form of a XY diagram. The x-axis of the diagram shows the time. Time is an important attribute in the validation, as we want the pressure to be equalized as quick as possible. The y-axis shows the pressure in millibar within the enclosure. The lower the pressure, the lower is the stress on the enclosure and the seal. Without a vent, the internal under pressure will reach approximately minus 150 millibar. This force can harm the gasket and cause leakages, which can in worst case lead to a failure of the device. Even the use of a very small adhesive vent will already improve the situation significantly and minimize the pressure to only minus 22 millibar. Preferably, we should aim towards zero pressure. The green line represents a vent with a higher airflow rate that allows a very quick equalization of the pressure. This is the ideal situation. There's a variety of integration options available. Most common ones are screwing, snapping, adhering, and welding. You can make your choice depending on your preferred integration method and application requirements. In summary, I want to underline that venting can make a big difference for the durability and lifetime of your sensor devices, and that it is recommended to be considered early in the design phase of your device. With that, I want to say thank you for your attention and wish you success with your future sensor developments.